Hello everyone, welcome to the presentation. I am Dhruv Deshmukh and I will be presenting the topic Primal-Dual algorithms for connected facility location problems. Uh, in this I am going to mainly discuss a paper that is originally written by Chaitanya, Swamy and Amit, Kumar. So let me just introduce the problem to you. The name of the problem is Connected Facility Location Problem. So in this we are given a graph G with V as the set of vertices and E as the set of edges. In this we have a set of facilities F, which is a subset of V, and a set of clients D, which is again a subset of V. What we want to do is to open facilities at uh, some vertices present in the set F and assign each of these facilities to one of the clients. Further, we also want to connect these facilities by a tree, and the cost of that tree must be minimum. The facilities can have opening costs. That is, if you want to open a facility at a particular point, we have to pay a cost. So, to illustrate this, let me use this example below. Here we have these facilities F1 and F2, and these are the different clients D1 to D5. And in this particular graph, we have allocated clients D2, D4, and D5 to this facility F1, and D1 and D3 to facility F2, and finally F1 and F2 are connected by a tree where V is the root vertex. There are some other things like these H weights D2, D4 and D5. I'll explain them in the further slides. So as I mentioned, there will be some kind of cost and we want to minimize this cost. So first let's understand what the cost function will be. So the first term here, which is sigma of Fi over for I element of all the facilities. So what we have to do, what this is it is the uh, cost of opening facilities. So if when we open some facilities, what will happen is that the sum of all these facilities will add up. Then the second is uh, the demand cost per client. So here dj is the demand of a customer, and c I of j is basically what I of j means is that I is the facility and j is the customer. So I of j means the facility that has been allocated to customer j specifically. So that particular we have to take the cost of h between that particular facility and the customer, and then multiply it by dj and sum all of them up for all the customers in d. And finally we have this in this summation is the cost of the edges of the tree, and this particular constant m which is given to us. So finally the sum of all these is our cost function, and we want to minimize this. One point to note here is that this cost of edges that we are using, it's a metric, that is, it obeys triangle inequality. So now these in the earlier figure that I had shown you, these edge weights now make sense. So D2, D4 and D5 are basically the demands of the customers. For the customers D2, D4 and D5, and finally the edge weights are CE1 and CE2, and we have the F1, small f1 and small f2 as the opening costs for capital the facilities F1 and F2. So if the problem is clear and the cost function is now known to us, let us like come to a real world application, because you might be wondering why are we solving this problem in the first place. So this has a real world application, and that is in the telecommunication network design domain. So in this what we have is a central core, and there are a set of end nodes. So what we want to do is basically and one more point is that this particular central core consists of a set of interconnected core nodes, and each of these core nodes has some switching capability, and thus each of the core nodes has some kind of a switching cost. And what we have to do is we have to select a subset of core nodes and we want to connect them to each other, and also we want to connect these end nodes to these core nodes. So if you can see the analogy here, the clients are basically the end nodes, and the facilities will be the core nodes, and the switching cost that I mentioned is nothing but the opening cost. So basically this particular problem that I just told you can be converted to the ConFL problem and solved. Now let's come to a special case of this problem, which is known as the rent or buy problem. In this, what happens is we set the opening cost of all the facilities to 0, and we have this thing that the set of facilities is equal to the set of vertices, which means that we can open facilities anywhere in the graph. And another assumption that we make is that we know our root facility V, that is, we know that we are going to open a facility at this particular location. Now let's discuss some applications of the rent or buy problem. So one application is in the data management and caching problem. So here what is happening is that we want to store certain data objects, and we will store them at multiple nodes, and users will issue read and write requests to get these data objects. Now what we want to do is store these objects in these nodes in such a way that we have the minimum cost for read and write operations. So this I'm not going into the details, but if you want to model this, you can model it as a ConFL kind of a problem. Another application is in the VPN provisioning. That is, what we do is we have different VPN endpoints, and they have a upper bound of the incoming and outgoing traffic. So what we want to do is assign the VPN users to each of these VPN endpoints and connect them to each other. So again, if you are able to see the analogy, it's similar to ConFL problem with a rent or buy simplification. That is, we can have endpoint anywhere. Now let's come to the earlier works that have been done on this kind of problems. So there already exists some constant factor approximation algorithm given by some other people, but the thing is that the number of constraints in this kind of a problem is exponential in nature. And another one is a combinatorial algorithm, but the approximation factor is even worse as compared to the LP solution, that the first one that I mentioned. So what the people in this paper have done, they have suggested a Primal-Dual algorithm for which has a 8.55 approximation ratio for the ConFL problem, and they have given a 4.55 approximation algorithm for the rent or buy problem. Now in this particular presentation, I will only discuss on the rent or buy problem in detail. The rest can be found in the paper. So let's introduce you to this particular algorithm for the rent or buy problem. So in this, we are going to make a simplifying assumption that the demand DJ for all the customers or clients is 1. So the algorithm actually consists of 2 phases. The first is the clustering phase, where we actually map each client to a facility or assign a facility to each client, and the second is constructing a Steiner tree that will connect all these facilities and week that we have opened. And one more simplifying assumption that you are making, and this will be used while solving the problem, but after solving the problem, I'll also tell you that even if we remove this assumption, the solution that we have obtained will still be valid. So this particular assumption is that the facilities can be opened anywhere along the edge. That is, if we have an edge UW, then you can open a facility at any point on the edge between U and W. And these internal points on the edges that I just mentioned and all the vertices, these together are called locations. So we will not call them facilities, we'll call them locations. And the metric that we had put on the cost of edges will now extend to these locations as well. So how will this happen? Let me tell you. So how this simplifying assumption is made to obey the metric is that for any point P on this on an edge, say edge is UW, the distance CUP will vary continuously and monotonically from 0 to CE. So you can imagine that as the point P is getting further away from U, the cost CUP is increasing. And what we can say is that CWP will be equal to CE minus CUP. So it's just simple subtraction. The total cost minus the cost from U to P is the cost of W to P. Now for any vertex R that we take, which is not equal to U, pardon for this mistake, here I mean to say R is not equal to U or W, what we can say about CRP is that it will be minimum of the cost from R to U plus cost from U to P dash, comma C of RW plus C of WP. So basically this P is lying between U and W, and R is some outside vertex. So we can reach this point P via U or via W, and thus we have two different paths with two different costs. We will take the minimum of them. And similarly we can define it for any 2 points P and Q which are lying on two different edges. So say P lies on E1, that is UW, and Q lies on some other edge E2. So the cost CPQ can be again modeled using the same thing that we did for R, that is it will be CUQ plus CUP dash, comma CWQ plus CWP dash, the minimum of these. That is again we have two paths from P to Q, that is one is via U and one is via W, and we take the path with the minimum cost. So if the problem is clear to you, first let us see the LP formulation for the CON-FL problem, and then we'll see how it simplifies for the rent or buy problem in our case. So the cost function, as I had explained you earlier, will be this, but in this now we have the variables added. So yi is the variable for whether a facility I is opened or not. So if y will be 1 if a facility is opened at I, and it will be 0 otherwise. And xij is the variable that says facility I is assigned to client J. So if a facility I is assigned to client J, then it will be xij will be 1, otherwise it will be 0. And finally ze is basically if the edge E is picked in our tree, or then it will be 1, otherwise it will be 0. So the first term is basically we go over all the facilities and we multiply yi with fi. So automatically only those facilities that are chosen, their fi's will be added, and we'll get the first term of our cost function. Then in the second part, what we are doing is, first we are going to the inner sum. We are taking a particular client, a particular facility, and so what we'll do is let's go from left to right. So we are summing over all j. So for a particular j, that is for a particular client, we are multiplying his demand, and multiplying his demand by the summation of I Cij Xij, that is whichever facilities this particular client is connected to, we take the cost of edges between that facility and the client, and we add them up to get the cost, and then we multiply each of them by dj, and then sum over all the possible clients to get this second cost, that is the demand cost. And finally this is the cost of the tree. So for every edge in the tree we multiply by CE, so automatically those edges in the tree will come over here and sum up, and then multiplied by the constant m. Now coming to the constraints. So this first constraint ensures that for, every client is allocated to at least one facility. So you can see we are for a particular client we are summing over all the facilities, and at least one of the xij has to be 1, that is at least j has to be assigned to at least one of the facilities, then only this constraint will hold. The second constraint is that we must assign like if we are assigning a particular client to a facility, then the yi, that is, we have to open up the facility there. So this must hold for all I and j. This inequality. So that is, if this is 1, that is, we are opening a facility at I, then automatically it has to be less than I. So if we are not opening a facility at I, then xij will be 0. That is, we cannot assign client to that facility because we have not opened it. Then this is an obvious constraint, because we have said that we know that we are going to open a facility at v, y of v must be equal to 1. And this final constraint is for the Steiner tree. So what we are saying is that if we take any cut of this graph that separates the that separates v from that separates a particular facility from the root vertex, then what should happen is that there must be at least one edge that goes across the cut. That is, it will connect the facility to the root vertex v, and here we are extending it. We are saying that for all the clients, if we take a particular set of vertices, and in that we have certain facilities to which these clients are allocated, then this set and the other set will consist of the root vertex v, and the cut across it must have at least one weight. So we are ensuring that whatever facilities we are taking in this particular set, there is some path connecting these facilities to the vertex v, and thus ensuring that the graph that we are making among the facilities is a tree. And here again, like all these variables will be 0 and 1, and we can relax it, this ILP to the LP, that is where all of them will be just greater than or equal to 0. Now coming to the rent or buy problem, the simplification that will happen is that because we can open facilities at any particular vertex, the y term, that is whether we are opening a facility at a particular location or not, will disappear. We are basically assuming that we have open facilities at every location. Finally we will not do that, but in our cost function we no longer need to have this variable y I, because there is no cost for opening the facility, and hence the constraint, that term is disappeared in the cost function, and also the constraint that had this yi has disappeared. And finally the dj that we is equal to 1, the assumption that we made. So this is the final LP for us. Coming to the dual of the LP. So the first, in the previous slide we saw the primal, and now we want to construct the dual. So here what we have is two set of constraints. One is for all j, and the second one is for all s and j. So we'll have these two set of variables in our dual, but in the cost function, if you see for the dual, only the first one, that is alpha j, that is coming into the picture. The theta sj variable, that is for all s and all j, is not coming into picture. This is because in the second constraint, if we move the term on the right to left, the constant here becomes 0, and if you know the standard process of converting a primal to a dual, because of the 0 factor, the second variable will not come in the cost function. It will go to 0. Now the constraints that to explain are, the first constraint is basically alpha j. Here is basically the payment that we are willing to make for j, and part of this payment will go in connecting j to a particular facility, and the other part of the payment will be connecting the facility to the root vertex v. In case of the root vertex, this particular second cost will not come because v is the vertex itself, so we only have to pay the cost for connecting it to v. And the final constraint is ensures that the cost we are paying to connect it to vertex v is less than equal to the cost of the edge that is used, scaled by m. So now we have understood the dual. So let's start the phase 1 of our problem, which is clustering. In this, what we will do is start raising the alpha j demands, alpha j for all the demands. We'll increment them at unit rate, and finally at t is equal to finally we'll stop the process when there's nothing left to increment. So I'll explain this. So initially at t is equal to 0, v is tentatively open and all other locations are closed. Tentatively open means that finally all the locations that we open using this particular method will not have open facilities. Only some of them will have open facilities, other locations will be dropped. So at some let's move ahead. At some point what will happen is, for a particular demand j, this constraint will become tight at a particular location I. So that is alpha j will be greater than or equal to Cij. Why just Cij? Because here we also have the other part, but what we are focusing here is the clustering. That is, we are just focusing on assigning j to a particular facility, and we are not focusing on building the tree. So hence we are not focusing on the other part of this constraint, and to make sure that the constraint is still obeyed, we are going to increment this right hand side simultaneously for all sj. So as basically for all sj, in the sense only sj, sj is the set of vertices which is for which j is tight at some point of time. So for any particular location where it is becoming tight, it will come under sj, and for this set of vertices we will increment theta sj at the same rate, so the constraint will be maintained. Now we have that the states can for the demands can be frozen or unfrozen. So when a demand gets frozen, we stop incrementing its dual variable alpha j, and till it is unfrozen, then at any particular time t, we can say that the alpha j is equal to t. Initially all the demands are unfrozen, and finally what will happen is all the demands will be frozen and will stop. But when will these demands be frozen? Like, what are the conditions? So the first condition is that we have a we have already opened a particular tentatively opened a particular location I, and j becomes tight at this location. Then we will freeze j, because now why will freeze j? Because now j we can assign j to this already opened location I, and we will meet our demand in that case. The second one is that the location I is closed, but at a particular moment what will happen, at least m demands become tight at it. That is, there will be intersection. I'll explain this in a figurative manner in the next slide. So m demands simultaneously get tight at this particular location I. So the demand m that is there in our problem is meeting, and so we'll open I tentatively, and now what we can do is assign all these demands, that is customers, to this particular facility I, and thus make them frozen. So let's take this as a example to understand the process that I just explained. So at t is equal to 0, only v is tentatively open and represented in black. The other squares blue are the other possible locations for facilities, and they are tentative, they are closed as of now. And 1, 2, 3, 4 and 5 are the demands or the clients. So at t is equal to 1, you can visualize the alpha j as the radius of circles, and we'll increment the radius of these circles one at a time. So at initial point there is no constraints are becoming tight. Now at t is equal to 2, you can see that for 1, 2, for 1 it is becoming tight at 2 locations, for 2 it is becoming tight at 1 location, and this location is common with 1. And in our this particular instance of the problem, we are assuming m is equal to 2. So at this location that has become black, now you can see that 2 demands are getting met. And so if we go by the second condition, we have m demands, that is m is equal to 2, are tight. So we will tentatively open this location, and hence it has become black, and we'll freeze them. You can observe that the other location for which it was becoming tight for 1, we do not open, because m is equal to 2 and only one one demand is being met, tight, becoming tight over this point. Same for 3, it is becoming tight at this location, but because the demand over here is not met, that is m is not equal to 2, it's less than 2, we will not open a facility over here. Now at t is equal to 3, the circle for 3 has expanded even more, and it has come to this particular point where we are already opened the facility. So here the first condition will apply, that is j has become tight at a tentatively open location, and hence j will become freeze, because we'll assign 3 to this already open facility. And the case for 4 and 5 is similar to that of 1 and 2 in at t is equal to 2, so I'll not explain that again. So finally, which locations do we open? That is, we said that we tentatively open these locations, but finally we are going to open facilities at only particular locations. So we'll see here how to choose these locations. So let's first define some terminology. L is the set of all the tentatively open locations, and for any two I comma I dash which are element of L, we call them as dependent if there is some particular demand J which is tight with both of these locations. So here in this case, one had become tight at both two locations. Now one of the locations we didn't open tentatively, but say that it was also opened, then what will happen is both of them will be part of L, and for both of them one is becoming tight. So hence we will call these two locations to be dependent in that case. Currently they are not dependent, but this could have happened. Now what we want to do is first we'll define what is set of locations that is independent. So set of locations is independent if there is no two locations that are dependent in that set. We want to construct a maximum independent set L dash from these locations L, and how will we do is as follows. It will be a greedy kind of approach. We'll arrange the locations in an increasing order of like how they were tentatively opened, increasing order of time basically. And finally what we'll do is for a particular location we'll check if there is any location in L dash that is already dependent with it. If not, then we'll add it to the L dash set, otherwise not. So finally we'll get this L dash set, and we can see that if dependency exists, we are not adding that location to L dash, so L dash will be an independent set. And this particular L dash now is the final set of locations where we open the facilities. And you can notice that V will always be in it because it is the first location that is open, so always put V in L dash. Now this only told us which facilities, which locations to open facilities at, but we also need to assign the demands to the facilities. So how to do that? So here we'll have two cases. First case is that J is tight with some I which is already in L dash. So in that case we'll just assign J to I and we are done. The second case will be that this particular I is not in L dash, but it caused I to be but this I caused J to be frozen. So why did I not end up in L dash? It would have happened because there was some I dash that opened before it, and they were dependent. So hence I dash was added first, and then I came, and because of the dependency it was not added to L dash. So in that case what we'll do is assign J to I dash. This is how we'll do the assignments. And finally this is some notation. So we are saying that sigma J is like says that this particular location is assigned to J. So now what? So now we are actually we have completed the phase 1 of clustering, and we now need to build a Steiner tree on these set of vertices L dash that we have got. So for that we need to first augment our graph, because as I said, we can open edges on any of like we can open facilities on any of the edges, any point on the edge. So we'll have to include these non-vertex locations as well in the graph. Say I1 to Ik were the open locations on edge E, U, comma W. So we'll order them from U to W. So first we'll have edge U I1, then we'll have I1 comma I2, then we'll have Ik minus 1, finally Ik, and then finally Ik to W. This is how we order the edges. Now let's start with the Steiner tree. How will we build the Steiner tree? So again, some notations. First is that for any location I, we define this particular set D of I. It denotes the set of demands that became tight with I. Okay, and then we define set D, which denotes the union of all those DIs except of V. So V is the root. So except of that, all the other facilities which we opened, that is I element of L dash minus V, we take the union over all those DIs, and we set alpha j to 0 again for all the j, and we start increasing alpha j values for only the demands that are present in D. Okay, so and then what we are doing is we are just going to simulate the Primal-Dual algorithm for the rooted Steiner tree problem. So let me just briefly tell you about this algorithm. So we have this minimum violated sets or the singleton sets for all I which are element of L dash minus V, and now like the visualization will be same. We have these radius circles of radius alpha j, and we are going to increment them one by one, and finally whenever there is some intersection, this is the only case here alpha j is not the thing, we are actually incrementing theta sj. So this is for the facilities in this case, facilities that we have. So what happens is that we define another notation over here. So for a particular set S, we define ds as the union of, so we take all the facilities that are opened and that are in S, and we take the union over all the DIs of these open facilities, and that is defined as D of S. Now what we do is for any MVS S that is there, that is the violated set, any client that is in it, we raise its value of alpha j at the rate of 1 by ds. So that is the size of that set, and we also increment the dsj by the same rate. So what will happen is for every j in that s, we are incrementing it at this 1 by ds rate. So if we add it all up, finally the whole summation of theta s comma j will grow at rate of 1 for any particular s. And in this particular section of the phase 2, we are not going to check if constraints 2 or 3 in the dual are being obeyed. We are only going to ensure that the constraint 4 is obeyed. Okay, and finally whenever there is a tightness, the constraint 4 will become tight. One of the constraint in set 4 will become tight. We will basically add that edge to our tree and update the sets, and finally we will keep on doing this when till the number of violated sets becomes 0, that is we have a single component that is left. And then what we'll do is we'll consider the edges in the tree in the reverse order in which they were added, and remove any redundant edges. That is, already we have got a connection and we don't need any other edge. So finally we'll have a tree, Steiner tree. So yeah, that is the algorithm. So we first clustered, that is we using the greedy approach, and in like this visualization of increasing circles of radius around the clients, we first clustered the clients by assigning them to the facilities I, and then we did not open facilities at all the locations, we only opened at particular locations, and finally we got, once we had got the set of open locations, we did the Primal-Dual algorithm for the Steiner tree and got our solution. So we had two problems. One is this phase 1 problem and phase 2 problem. So let the solutions alpha 1 theta 1 and alpha 2 theta 2 be the two solutions for phase 1 and phase 2, and these are for the dual. This is for the dual problem. In this, one should note that the dual solution alpha 1 theta 1 is feasible. I'll not go in its proof, but it is feasible. Now if we are the second case is that the Steiner tree algorithm that we used has approximation ratio of 2, but if you use a better algorithm, then it can be reduced to 1.55 approximation ratio. Finally, if we prove that in phase 1 the assignment cost that we are getting is at most 31 alpha 1 j, that is the optimal solution, optimal LP solution for the dual, then we have proved that finally the 1.55 plus this 3 gives a 4.55 approximation algorithm to us. Now let's come to the proof that clustering gives a 3-factor approximation. So first case here will be that if j is a demand that became tight at location L dash. So in that case we can say that for this location I, C of ij is less than equal to alpha 1 j is less than equal to 3 alpha 1 j, so we have no problem. In the other case, j is assigned to I, but I dash is a location that tentatively open facility for which j become frozen, but I dash didn't open end up in L dash, which means there is some other facility I in L dash on which has a dependency with I dash. So this will happen because there is a demand k which became tight at both I and I dash. So T of I and T of I dash are the times at which I and I dash opened tentatively. Now first one thing is that J became frozen at this particular facility I dash. So it is clear that alpha J must be greater than T of I dash, because at this point the freezing happened, so it has to happen after that, because if ti dash is opened before, then like if it is other way around, then it means that the facility was not open and the constraint became tight for j, so I dash was not opened at all at that time, so which is a problem. We are saying that I dash was opened and j became frozen, so alpha 1 j has to be greater than or equal to ti dash. Secondly, we can say C of ij is less than equal to C of I dash plus C of I dash j, and we can further split I dash as C of ik plus C of ki dash. And this we can write as, because we are having tightening at I and I dash, so we can say for Cik and Cki dash 2 alpha 1k, and we have tightening at Ci dash j for j, so we can say alpha 1 j there. Now other thing is that alpha 1 k must be less than equal to T of I dash. Why is that? Because if it is greater, then we know that I opened before I dash, so T of I is less than equal to Ti dash, and that is in turn less than equal to alpha k, which means that that k is tight at both I and I dash at T is equal to alpha 1k. But if that cannot happen. Now let's come to the second case, that is it is in between, that is Ti then alpha k and then Ti dash. Now that can again not happen, because if that happens, then alpha k will become alpha k will become means I is already tentatively open and alpha k becomes tight at I, then it means k will become frozen and it will never go on to become tight at I dash, and then it's a problem for us. So basically we have the final case, that is alpha k has to be less than both of them. that is t of I and t of I dash. So if that is the case, then using the above equality of alpha j being greater than ti dash, we can say that ti is between alpha k and alpha j. So alpha k is bounded by alpha j. So in the above inequality, we can substitute 2 of alpha k by alpha j, and finally we have 3 of alpha j. So we thus prove that the clustering is basically giving us Cij less than equal to 3 of alpha j. That is the optimal dual solution. And from Steiner tree we have the 2 or 1.55, and thus adding them gives us the 4.55 solution. But wait, there is a problem. The assumption that we had made allows us to open facilities at non-vertex locations as well, and that is not allowed in our case. So we need to first solve that problem. So how will we do that? So let's consider an edge E on which at an internal point a location has been opened. So D is the set of demands that was assigned to let D be the set of demands that was assigned to such locations. Now in this some set of locations will be assigned through U, so they will have cost lesser through the U path, so let's call them DU. And there will be some locations which have lesser cost when we go through W, so we will have DW for them. Now in our case, if both you, at least one of them has to be in our case, because we have to finally reach this location in our tree. So that we'll only be able to reach this location if at least one of U and W is present in the tree. So if both of them are present, then the solution is simple for us. All the locations in DU, like non-vertex locations in DU, will assign to U, and all the non-vertex locations in DW, that is in DW, will assign to W. And in this case, no cost will increase, because basically we are not going that extra part of the edge from U to that particular point. We are stopping at U itself. So the cost of tree is only going to decrease in our case. So that is better for us. And if say the case is that U is in the tree and W is not in the tree, then what we will do is um, we'll take, let L be the location that is farthest from you. Now what we will do is we'll see if the demand at W is less than M, then we will assign DW as well as DU to both of them to U, and we'll remove all the edges in T that lie along the E, that connect them, that connect these points to through W. And if that is not the case, so if the demand at DW is greater, so we have no problem at opening facility there. So we'll reassign all the edges to W, and U is already there, so no problem assigning them. Finally, this basically like easy to see that the cost is only going to decrease. We are not traveling that extra distance along the edge. We are stopping at U and W itself. So the cost is only going to decrease for the tree, and hence we can shift all these vertices which were at non-vertex locations to actual vertices, and convert our solution to a valid one. So that's it. That explains the whole algorithm for the particular case of rent and buy problem we discussed. Hope you understood and enjoyed. Thank you.